Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. This is section 11.2 series. We studied telescoping sum series and geome- uh, geometric series. In both cases, we can find Sn, and when we find Sn, the nth partial sum, we can determine whether the series is convergent or divergent. Now, we mentioned that there are three sequences. We talked about them. The sequence an. Now, if we have a series like this, summation an from n1 to infinity, the sequence an, sequence of terms of the series. Now, this theorem will give us a relation between the series and the sequence an. In the previous two lectures, we discussed the relation between the series and the sequence Sn. This theorem says if the series is convergent, the limit an when n goes to infinity is 0. And notice that it is if then. So the converse of the theorem is not true. And we mean by the converse is not true in general, that if the limit is 0, this doesn't mean that the series is convergent. If the limit of an is 0, we cannot conclude that the series is convergent. For example, the series square 1 over n, summation 1 over n, this is the harmonic series, and this series is divergent, although an is 1 over n, and the limit of an when n goes to infinity is 0. So limit of an is 0, but the series is divergent. So the converse is not true, which means if you find the limit of an and you find that it's 0, you don't conclude that the series is convergent. It could be convergent or could be divergent. No information is given here. And remember that with any series, there are two sequences associated. The sequence Sn, partial sums, and the sequence an of the terms of the series. If the series is convergent, then the limit of Sn is S, which is the sum of the series, and limit of an is 0 according to this theorem. Now, the contrapositive of the statement is always true. And what is the contrapositive of the statement? You start from here, but with negation. So you say that if limit an is not 0, then the series is not convergent. This is called the contrapositive of the statement. And this will be called test for divergence. So what is the test for divergence? If limit an is not 0 or does not exist. Not 0 included, uh, also does not exist, infinity for example. So if limit an does not exist or not equal to 0, then the series is divergent. And this is a very easy test to check immediately whether the series is divergent or not. Just find the limit of an. So for example here, show that the series is divergent. Find limit of an, which is n square over 5n square plus 4 when n goes to infinity. And if you remember, we find this limit by dealing only with the highest power, the term with the highest power up and down, and the limit would be 1 over 5. And this is not equal to 0. So by test for divergence, series is divergent. So this is the proof that the theorem proof that the theorem the series is divergence. So if we find that limit an is not zero, we know immediately that the series is divergent. But if we find that the limit of an is zero, then we have nothing, no information about the convergence or divergence. So we will use other tests in the coming sections to determine if limit an is zero, to determine whether the series is convergent or divergent. Let us look to this example. This is a sequence an. Determine whether the sequence is convergent or not. This is section 11.1. The sequence would be convergent if the limit of an when n approaches infinity is a number. If we find the limit here when n goes to infinity, it would be 2n over 3n cancel n with n, so it would be 2 over 3. So yes, the sequence is convergent according to section 11.1, the definition of convergent sequences. Now, is the series convergent? Where an is the same an here. So the answer is no. Series is divergent by tests for divergence, since limit of an when n goes to infinity is not zero, because we found limit of an in part A and it's 2 over 3, it's not zero. So by test for divergence, this series is divergent. So pay attention to the difference between series and sequence. Convergent series, if two series are convergent, then their sum is convergent, their difference is convergent. Multiplying by a constant, a number, is also convergent by a constant. Find the sum of these two series. When he says find the sum, it means that this two series must be convergent. So the sum of the two series would be the sum of the first one plus the sum of the second one. You can deal with them as two different series. The first one can be written as a telescoping sum series. So you can talk about Sn, and Sn is summation I from 1 to n ai. An is 3 over n times n plus 1. So this is 3 over I times I plus 1. And now you write 3 over I times I plus 1 as A over I plus B over I plus 1. And you can find, if you replace I by 0, that A is 3, and if you replace I by -1, B is -3. So you can write this as summation 3 over I, because A is 3, and minus 3 over I plus 1, because B is -3 from 1 to n. And this is a telescoping sum. If you now write the first two terms, 3 minus, if you replace I by 1, 3 over 2, this is the first term, plus, if you replace I by 2, 3 over 2 minus 3 over 3, or 1 plus plus. These are the first two terms. And the last two terms would be, when you replace I by n minus 1, you will have 3 over n minus 1 minus 3 over n minus 1 plus 1, which is n. And when I replace I by n, I will have 3 over n minus 3 over n plus 1. And you can notice that here 3 over 2 cancels with 3 over 2. So the second term will be always cancelled with the first term of the next term. And here at the end, I notice that uh, 3 over n will be cancelled with negative 3 over n. So the first term here of these two will be cancelled. So also this one will be cancelled with this one. And at the end, I will get only 3 minus 3 over n plus 1. So this is Sn, the nth partial sum of the first sequence. And now if I find limit of Sn when n goes to infinity, it would be 3 because 3 over infinity is 0. So the sum of the first sequence of the first series is 3, while the second series is a geometric series. And let us write it as uh, it starts from 1 to infinity. So I'd like to write it as to the power n minus 1. So I can write it 2 times 2 to the power n minus 1, which will give you 2 to the power n. And now a is half and r is also half, and it is less than 1. So the series is convergent, and the sum is a, which is half, over 1 minus r, which is half. So half over half is 1. So sum of the series, the original series, which is 3 over n times n plus 1 plus 1 over 2 to the power n from 1 to infinity, would be the sum of the first series, which is 3, plus the sum of the second series, which is 1. So the sum is 4. This is an important note. A finite number of terms doesn't affect the convergence or divergence of a series. A finite number of terms. So for example, if we are able to show that this series where n starts from 4 is convergent, then the series, the same series, when n starts from 1 would be also convergent, because it would be from 1 to 3 plus from 4 to infinity. So from 1 to 3, just 3 terms. So if you add 3 terms to a convergent series, it would be also convergent. It will not go to infinity. So uh, if you know that from capital N plus 1 to infinity is convergent, if you know that this series is convergent, if you can prove that this theorem is convergent, then if you start from 1, these capital N terms in the beginning will not affect the convergence, and this series would be also convergent. Also, same you can say for divergent series. Determine whether the series is convergent or divergent. If it is convergent, find its sum. Well, here, look to the second term. 6 is 2 times 3. 9 is not 2 times 6. So this is not a geometric series. But for the first term, this is 3. And here it is second term, it's 2 times 3. Third term, it's 3 times 3. Fourth term, it's 4 times 3. So it seems that an is 1 over 4 times n. So this is the sequence. This is this sequence from 1 to infinity. This is the sequence, okay? So if you put n 1, you get, well, not 4n, 3n. If I put n1, I get 1 over 3. If I put n2, I get 1 over 6, yes. So this series is summation 1 over 3n from 1 to infinity. This is a sequence, okay? The nth term of the sequence, but this is now the series, the summation of the sequence. All right, we know that 1 over n is a harmonic series. So this 1 over 3 can be taken out, and you can write like this. And this is multiple of the harmonic series. And we know that the harmonic series is divergent. So multiple of the harmonic series would be divergent. Here, for the first term, when n is 1, I have 2 over 5. When n is 2, I have 2 square over 5 square. When n is 3, I have 2 cube over 5 cube. So an here is 2 to the power 2 over 5 to the power n. Okay, if you put n1, 2 over 5. If you put n2, 2 square over 5 square, and so on. So this is summation. This series is summation 2 over 5 to the power n from 1 to infinity. Now, it seems that it is a geometric series, but let me write it since I'm starting from 1 to infinity. Let me write it 2 over 5 times 2 over 5 to the power n minus 1 to compare it with a times r to the power n minus 1, the form of the geometric series. So a is 2 over 5 and r, the common ratio, is also 2 over 5. So less than 1. So this series convergent and the sum is a over 1 minus r. And if you divide these two numbers, you just get 2 over 3. So that's the sum of this sequence, of this series. Well, here, it is not a geometric series. It's not number to n to the power n. It is not, it cannot be written as telescoping sum. It's not telescoping sum. So let me find limit of an, and let us from now on always when we discuss the convergence or divergence of a series, begin always by finding the limit of an when n goes to infinity. And as usual, we take the terms with the highest power, so the limit would be negative half, and this is not equal to 0. So by test for divergence, this series is divergent. Well, here I have number to the power n, so this seems to be a geometric series. It starts from 1, so let me write it as, this is 3 to the power n plus 1, so it would be 3 times 3 times 3 to the power n minus 1, because I need n minus 1. Okay, if you add, you get n plus 1. And 4 to the power negative n, I can write it 4 to the power n, and I can write it 4 times 4 times to the power n minus 1. So it would be 9 over 4 times 3 over 4 to the power n minus 1. And this is a geometric series with a equals 9 over 4, r equals 3 over 4, less than 1. So it's a convergent geometric series with sum equals a, which is 9 over 4 over 1 minus r, which is 3 over 4. And if you divide these two, you get 9. So the sum of this series is 9. Well, here I have two series. Okay, so the first one is negative 0.2 to the power n. And I can write it negative 0.2 times negative 0.2 to the power n minus 1. And the other one is 0.6 already to the power negative n minus 1. So both are geometric series with r less than 1 or absolute value of r. So they are convergent. And the sum of two convergent series is convergence. Well, for the first series, let me say this is S1 and this is S2. For S1, I have A equals negative zero point 0.2 and R is negative zero point 0.2. So sum would be A over 1 minus negative zero point 0.2 or plus zero point 0.2. So the sum of the first series would be negative 1 over 6. And the second series is 2. A here is 1 and R is zero point 0.6. So the sum is A 1 minus zero point 0.6 and this is just 1 over zero point 0.4 or 5 over 2. So sum of summation negative zero point 0.2 to the power n plus zero point 0.6 to the power n minus 1 is negative 1 over 6 plus 5 over 2. So that's the sum of the two series, 7 over 3. Well, here I have e to the power n, but I have here 4. So it is not a geometric series. So let me find limit of 1 over 4 plus e to the power negative n when n goes to infinity. Well, e to the power negative infinity is 0, so the limit is 4, and it is not 0. So by test for divergence, series is divergent because the limit of an is not 0. Well, here I can write it. Sum of two series. The first one is 2n over en. And the second one is 4 to the power n over e to the power n. And I can see that the second series, if you concentrate here, the second series, this one, can be written as summation 4 over e times 4 over e to the power n minus 1. And this is a geometric series with a equals 4 over e and r equals 4 over e. And 4 over e is greater than 1. So it is divergent. So this series is sum of convergent and divergent series. So this series is divergent. Let us find here the limit of len n square plus 1 over 2n square plus 1. We learned that we can take the limit inside the len, and then I take the two highest powers, two terms. So it's half, so it's len half. And len half is not equal to 0. So by test for divergence, the series is divergent or series diverges. Arctan, if I take the limit of tan inverse n When n goes to infinity, this is pi over 2. And this is not 0. So by tests for divergence, series diverges. Well, here, the first series, which is 3 over 5 to the power n, this is a geometric series. I can prove that. But I can see that 2 over n is multiple of the harmonic series. This series is 2 times 1 over n. And this is multiple of harmonic series. And the harmonic series is divergent. So this theorem is that this series is divergent. So this series is divergent because one of the two series is divergent. Well, here, if I find the limit, I have e to the power n. This could be geometric, but n square is not. So let us find e to the power n over n square when n goes to infinity. Well, it is infinity over infinity. So let me use L'Hopital, and let me deal with functions e to the power x over x square. E to the power infinity is infinity, infinity square is infinity, so I'm going to use L'Hopital's rule. The derivative of ex is ex, the derivative of x squared is 2x. If I replace x by infinity, I still have infinity over infinity. So I use L'Hopital's again. Derivative of ex is ex, derivative of 2x is 2. And now if I replace x by infinity, I get infinity over 2, which is infinity. The limit does not exist, okay? It is not equal to 0. So by test for divergence, the series is divergent or series diverges. This is the end of section 11.2. I hope you enjoyed studying series.